He's going to be giving us an invitation to the lifting decomposition.
So thank you so much for the invitation to talk. It's been such a great time. I've really learned a lot while I've been here. So this is an invitation to the lifting decomposition. And I think it's a very powerful and simple tool to use. And if you're interested in cat zero cube complexes, which you must be because you're here, then I invite you to learn and utilize this really cool technique. Okay, so an outline of the talk. We're going to review box sets and wall spaces, which were discussed last week. We'll define the roller compactification and boundary. And then we'll introduce the lifting decomposition and prove it. And then I'll give you some examples and uses, such as how the cat zero geodesic can give you a lifting decomposition. That's what I mean by LD. Also a probability measure on the roller compactification. And then also how this vaguely can be used to get an OT tilde equivariant simplicial structure on the Tits boundary. So OT tilde equivariant means that it's not equivariant on the nose, but it's homotopy. It's equivariant up to homotopy equivalence. Okay, so last week we had some really great introductions from Lazarovich and Fioravanti on Sageev roller duality and median spaces. And these are recorded, and I believe all of you have access to those recordings. So I encourage you to check them out, and you can always play them at double speed and then slow down if there's something cool, okay? So part one, box sets and wall spaces. So this is really a summary because again, these were discussed extensively last week. And so definitely the students know about it. And so we start off with a cat zero cube complex and we associate to it its half-base structure. These are going to be called this math frac H or math frac H of X if I want to emphasize what is the associated cat zero cube complex. And with the partial order given by set inclusion, this gives you a POC set. So POC set refers to a poset with complementation, namely that it's closed under taking complements and it has finite intervals. Okay, so associated to a cat zero cube complex, you can take its vertex set, and that's going to be X0. I'm almost always going to emphasize X0, but I might have forgotten it sometimes. And this is a median space with metric given as a discrete wall space, okay? So conversely, if you have a POC set with finite intervals or equivalently a discrete walled space, there's a canonical cat zero cube complex associated with it. And without getting too much into the detail of these definitions, let's just work through a couple of examples. So here I have taken this Venn diagram where all regions are supposed to be non-empty. And I'm going to take the equivalence relation where 2 points are equivalent if they belong to the same region. So associated to that, I have this cat zero cube complex where I connect regions if they differ by one partition. So this is a partition, two-sided partition. This is another, and finally that, okay? So I have 3, 5 walls. Similarly, over here, I have a similar setup. However, if you count the number of regions, I don't have the same number of regions as I have over here. And in order to make it a cat zero space, I have to sort of add this secret vertex in the back, okay? So with this structure in place, this canonical cat zero cube complex will contain the original space modulo this equivalence relation, but it may have additional parts. Okay, so this is a summary of discrete walled spaces or equivalently POC sets. And some references here are Sageev and Roller, Chatterji, Niblo, and Nika. Okay, so to summarize, cat zero cube complexes are incredibly useful and ubiquitous precisely because this construction is so flexible, okay? So I start with these types of partitions, and I get a canonical cat0 cube complex. So part 2, the roller compactification and its boundary. Since the half spaces separate points, we get an injection, a one-to-one map from the zero skeleton to this power set, 2 to the h, thought of as the power set, thought of as elements being sets, okay? So I have a map that takes x to the half spaces that contain it, and this is a one-to-one map. At some point, I will confuse the difference between a point x and the half spaces that contain it, okay? Now, this injection is a isometry in the sense that I have an extended metric on the power set, and that metric is given by the symmetric difference of sets. Remember, these are sets. And that gives you the distance. So 2 to the h is a compact space, and it's totally disconnected. I can take the roller compactification inside of 2 to the h, and this is the compactification. Of course, the roller boundary is you take the compactification and you remove the set. That's a pretty standard definition of a boundary. So I guess, is this, aha, there we go. So everybody's totally disconnected here. And if x is not locally compact, then it's possible that this boundary is not closed. However, the compactification is, of course, compact. So some facts about this compactification and boundary. If I have a tree, then the roller boundary, notice that I don't put a decoration on my roller boundary since it's my favorite boundary. Other boundaries will come up and they will have decorations, but not the roller boundary. So the roller boundary of a tree will be its Gromov boundary. However, the topology may be different, again, if it's not locally compact. So Z is the most interesting infinite tree, basic tree. And its compactification is, of course, plus or minus infinity. And the compactification has a nice product structure, namely that the compactification of the product is the product of the compactifications. And so we get that the compactification of Z squared is the product. And so we see that we have these flats at infinity. In fact, we have these corners, which correspond to the product of the two boundaries. And then we have these flats, like the sides, that correspond to the boundary across the space, and then also the space across the boundary. And those account for those flats at infinity. Flats meaning cat0 spaces. They may not be flats. Okay, so question, how do we know when a set, namely an element of the power set 2 to the h, is actually in the compactification? So the answer to that is that this set of half spaces should be consistent and complete, or maximal. I changed it from complete to maximal. So what does it mean consistent? It has two properties. Namely, if I choose a half space H, then I will not choose its complement, that is the opposite side, H star, which is defined there as X bar minus H. And if I choose a half space H and I have a larger half space, then I must also choose that larger half space. Maximality just means that for every pair of half spaces, opposite half spaces, I must choose one or the other. So observe that if I chose a random subset of X bar, that the collection of half spaces that contain it have to be consistent. That's just immediate. And we're going to see, this is the spoiler, that lifting decompositions essentially amount to this description with some nicer properties. Okay, so intervals are the first example of such a lifting decomposition. So if I choose 2 points, X and Y and X bar, I'm going to look at the half spaces that contain both. The intersection of all of those half spaces is going to be the interval. So I just, started drawing some cube complex. I think this is from another talk. I was on an airplane and I just, started drawing things. And so I've picked 2 points here, and this is the interval between them. Is there a question or? Okay. Similarly, the interval does not have to be inside the space if my point is on the boundary. So this is again z squared. This point is inside. This is one of the corners, and then this is the interval. Okay, so the interval doesn't have to be finite. Okay, so Cat0 cube complexes have projections. So if I start with a subset of the half spaces that is closed under involutions, that just means all of its every element has its opposite still inside of H. Then we can project from the compactification of X to the compactification of X of the associated Cat0 cube complex, where I just basically forget all of the half spaces in B. Okay, just pretend like they were never there. That's a new wall space structure, and we get a projection. Okay, so the projection is given exactly from the Bernoulli space 2 to the H to 2 to the H minus B by just removing that part. Okay, so when is this a section? Namely, so question, when is it a section, or when is it a retract? Same question. So let's look at an example here. I'm going to project the point Z to the interval, and that will always give me the median. Another example where you do not have a section, and I see some people going, what about that? Is this one. So here I have chosen 2 pairs of half spaces, and I'm going to forget them. So if I forget them, the associated wall space is this one. And as you can see, I can't come back because this has 3 edges coming out, and there's no such thing upstairs. Okay, so we always have this kind of projection. So now we're going to kind of understand when we can go backwards. So that's the, sure. Yeah. So this is coming from the canonical description of a Cat0 cube complex from a half space structure, right? So if I remove part of my descriptions, right? So yeah, okay. So it is a little confusing sometimes. So my description here is when is a set corresponding to a point. Okay, so a set is corresponding to a point when it satisfies these 2 properties. Now, H is all of the half spaces, okay? And I can remove some of those half spaces, and I get a new wall space structure or a new Poxet structure, and there's a canonical Cat0 cube complex associated with it, and I get this projection, okay? So that's already like very important. Item number 1 is this canonical description in terms of these sets, and then you can get this projection. Did I answer your questions? Great. No, it's a projection. It's a contraction. Yeah. I mean, this example here shows it's not an isometric embedding, right? But it is a projection. So exactly, we want to answer the question, when can we go backwards? Okay, when is it an isometry on something, and when can I put it back? Okay, and that's the whole point of the lifting decomposition. So proposition. So I'm going to take now, before I was just using a regular S, this is a fancy S because it's going to have a fancy property. It's not that fancy. So it's going to be a consistent set, okay? It may not be a maximal consistent set, but it's consistent, meaning, again, that if I choose a half space, I do not choose its opposite. And if I choose a half space, then I also choose anything larger than it, okay? So with this in place, it's not hard to see that S is disjoint from its opposite. So I'm going to remove S and its opposite. That's a well-defined half space structure. I have an associated cat0 cube complex. I have an associated projection. But the point here is that I can go backwards. I can bring this back, okay? And it's possible that the inside of X of HS may land on the boundary, okay? So it's really important that I'm working on the compactification here. And so this is an isometry. Now, what image is this? It's exactly the intersection of the half spaces in S. And the ... is intended to mean that there's more there, but actually almost everything that I'm discussing, there's more to, and I'm just trying to really highlight the role of this lifting decomposition. Okay, so even though the credit here goes to me and my collaborators, really this can be seen in a lot of earlier work. So I would say the real contribution that we're doing here is sort of uniformizing a lot of different examples that were already around and looking at the compactification where you don't have to make additional assumptions on the S, such as the descending chain condition. So let's do not quite a proof, but a little bit of a proof. So how does consistency give you that this intersection is not empty? That's like the first thing you want to know, right? So half spaces have a pairwise Helly property, which means that if they have pairwise non-empty intersections, then they have finite non-empty intersections. But X bar is compact, and so by the finite intersection property, you can go from finite intersections to infinite intersections. And then I left it as an exercise. It's really straightforward that consistency gives pairwise intersections. So to summarize, pairwise Helly property together with compactness gives you that this total intersection is non-empty. Okay, some other ingredients of the proof, other than knowing that the intersection is not empty, is knowing that if you have a consistent and maximal set, then you can remove everything in S union S star and then throw back in S. And this is, again, consistent and maximal. And then the section is an isometry, basically because this is a general fact about sets. Okay, there's no geometry here. It's just like you can Venn diagram that. And then again, as was observed by the audience, it's a really critical part that we have a canonical cat0 cube complex associated to this half space. So once we know how everything sits together and we know we have this decomposition, we know how half spaces decompose, then it's a canonical embedding back in. It's not an embedding, it's a canonical injection backwards, okay? So that's the lifting decomposition. So let's talk about some examples and uses. So Goralnik, going back to his thesis, described the following. So if I have a cat0 geodesic ray, I can look at its transverse or deep half spaces. So I didn't give you the proper definition because there's like an epsilon and an n, but it just basically says all of the half spaces that contain a deep and large neighborhood of the geodesic ray. And you will notice also here that I have passed from thinking of H as a bunch of vertices to now thinking of it as a cat0 space in its own right. And that's not the first time I will do that. So if I look at this Z cross F2 as an example, which I really spent way too much time drawing, then we have that it's elementary, meaning that it has a fixed point in the visual boundary, and that fixed point corresponds to, the direction that is sort of going, kind of coming at you, right? So the intersection of all of those half spaces will end up being the compactification of a cat-0 cube complex in this case, that is essential and non-elementary. So Caprace and Sageev, they showed that if you have a non-elementary essential action, then the essential core is non-empty and very, very nice. And so we were able to extend this to the roller compactification, namely, if you have an action by automorphisms, either it's roller elementary, meaning that you have a finite orbit in the roller compactification, or you have an essential core somewhere, such as in this example, where the essential core is the F2, and you may gain a kernel if you didn't already have one. Okay, so that was the first application. Now, a second application comes from some work of Mono and Shalom for trees, where we're going to take a probability measure, and we're going to look at the half spaces which contain more than half of the measure. So it's important to know at some point here and here in particular that all of the half spaces, I'm going back to the cubic, like vertex space on X, so X0. So those half spaces are clopen, they're open and closed. So if I look at these, in particular, they're measurable. So if I look at this heavy half spaces, the half spaces that contain strictly larger than half of the measure, then the intersection will not only, okay, so then this gives you a lifting decomposition, and the intersection is an interval, okay? So we have associated to a probability measure, could be quite wild, an interval in the roller compactification. So here's some examples. I have this cat-0 cube complex. I put 1, 6 at these 6 points, and then I get an interval here. Over here, this is z squared again. And I look at these 1, 6 measures, and then I get this as an interval. So you could play with a tree, take some very complicated measure, and you will get an interval again. Okay, so what did we use that for? Well, we use it for a few things, but in particular, if you have a co-compact irreducible lattice in SL2C cross SL2C or SL2R cross SL2R, then it cannot be cubulated. In fact, it can't even act non-trivially on a finite dimensional cat-0 cube complex. I think I forgot to say that all my cube complexes are finite dimensional, but I don't assume that they're locally compact or anything. Right. Another thing you can do with that is get a Tits alternative. So if I have gamma, this time, most of the time, I'm assuming that I just have a representation into the automorphism group. Now I'm really assuming that it's a subgroup of the automorphism group. Then either it contains an F2 acting freely, or it has an a finite orbit, and moreover, it's a power of 2. So power of 1 is a power of 2, 2 to the 0, so it could have a fixed point, or it has a power of 2. And that power of 2, that power is bounded by the dimension. Okay, what else can you do with that? Well, you can start with a generating probability measure on your group gamma. And given that generating probability measure, you can look at the associated Furstenberg-Poisson boundary. And with no assumptions on the space or the action, there is a finite index subgroup and a measurable gamma equivariant map taking the Furstenberg-Poisson boundary to the quote unquote regular points in the roller boundary, which I'm not going to define. Right. So this was previously known for free groups and perhaps some additional examples. This finite index subgroup essentially corresponds to the possibility that you have a finite orbit, and so you'll have to pass to a finite index subgroup maybe to go to I was thinking about how much time I have. to go to a fixed point. So you would theoretically, oh, sorry, this is a mistake. This is not, I was combining two theorems. This is to the roller compactification. And with some additional assumptions, such as non-elementary, you can get it that it's into the regular points. So this is actually into the roller compactification. Okay, what else? If you have an essential non-elementary action and X is irreducible this time, then the visual boundary will be, well, you can turn the visual boundary into a geometric model for the Furstenberg-Poisson boundary. And moreover, the random walk converges to the boundary. And yes, it converges to the boundary. Oh, that's what I wanted to say. It converges to a special type of point called a squeeze point. That squeeze point, I'm going to talk about a little bit in a little bit. It's going to be something that we can connect with the roller boundary. And the hitting measure is unique as a stationary measure on this visual boundary. So this had previously been obtained by Carlson and Margulis for more general, much more general cat0 spaces. Of course, cat0 cube complexes are cat0, but they maybe have no right to be, I don't know. And on the other hand, they put stronger assumptions on their random walk and the action. Similarly, some previous versions were obtained by Nebo and Sageev, assuming that the complex is irreducible and your acting group is a co-compact lattice. And again, I'm not assuming that the space is locally compact or much about the action. Okay, so why is it natural to start from a measure, understanding probability measures on your cat0 cube complex to the Furstenberg-Poisson boundary? I'm not going to say a lot about that, but it comes from the fact that the Furstenberg-Poisson boundary is Zimmer amenable. And this means that whenever your group is acting by homeomorphisms on a compact metrizable space, you always get a gamma equivariant measurable map from that boundary to probability measures. So for us, we're able to start to get control over those probability measures by associating the interval. And then the work goes into showing that almost surely those intervals are points. Points are intervals. Okay, so if you don't like measures, we're not going to see them anymore. So let's go back to this notion of a squeeze point. So what is a squeeze point? Well, I'm going to have a definition in the roller boundary and also a definition in the visual boundary. And they're sort of going to be in one-to-one correspondence. So I'm going to choose an element in my roller boundary, and I will say that it is squeezed if it contains, if it sits in this sort of structure of half spaces. Namely, I have, oops, I moved these things around, and this was supposed to be up there. So, so I can find a sequence of half spaces AN contained in BN contained in, so satisfying these inclusions. And the property is that AN and BN are sort of nicely controlled. It means that the bridge between them is quote unquote uniformly thin. It really means that there's one edge that takes me from this side in and then gets me back out on a different edge. And inside here, I have this like uniformly controlled set, whatever that means. And this comes from the fact that AN and BN are uber separated. I'm not going to define that either, but the bridge between them really looks something like this. And I have a uniform control over this. So as I look here, the distance between BN plus 1 and AN could be arbitrarily large or unbounded, as n varies, but I have control over these pairs AN and BN. So the definition for the squeeze points in the roller boundary is just that I can find such a collection, and their intersection gives me exactly, well, when I have such a collection, their intersection gives me exactly 1 point. It is sufficient to know that Y just belongs to the intersection. The properties are nice enough to tell me that nobody else is around. So then for the visual boundary, what does it mean to be squeezed? It means that it traverses in this deep transverse set, the cat-zero geodesic traverses these half spaces. So what happens? Because I have these bridges that are very narrow, if I start a cat-zero geodesic, say over here, and it goes past all of these half spaces, every time it goes through one of these bridges, it gets sucked in, right? So what happens is I have a unique cat-zero geodesic from a particular base point that traverses all of these. So what did we just do? We constructed a map that was X equivariant and in fact measurable from the squeeze points in the visual boundary to the squeeze points in the roller boundary. So can we go backwards? Yes, we can. Yes, we can. So how are we going to do that? We're going to take a half space again now as a cat-zero space, and we're going to fix a point in the roller boundary. We'll look at the intersections of all of those visual boundaries. And by the work of Caprace, and Balcer-Lichak, this is a non-empty set, closed, and it has a canonical circumcenter. So that's going to be our map. We're going to take Y to that circumcenter. And the observation is that, well, I guess I didn't tell you exactly what was going into these theorems, but their theorems are much more general, but they apply to us in this context. And so we didn't need, in this case, Y to be squeezed in order to do this construction. And here's an example. So I'm back to Z squared. I have that point in the corner. So all of the visual boundaries, so the half spaces that contain Y are the ones pointing to the right and the ones pointing up. So the ones pointing to the right have a semicircle as their visual boundary. The ones pointing up have a different semicircle as their visual boundary. And then their intersection is a quarter circle, and its circumcenter is pi/4. So the map here would take Y to pi/4, where the pi/4 is the point in the circle as the cat-zero boundary of R2. Okay, so now we're going to switch gears, and we're going to, any questions? I'm going fast. Yes. No, that's great. Go, yeah. Yeah, so no, I mean, this is like the super rigidity. So essentially what happens, maybe let me say something before I answer your question. So if I have a reducible lattice in those, then we know those are co-compactly cubulated. So going from reducible to irreducible is quite a big jump in that not only does it go from being like basically a cube complex to I can't even act. So coming back to your question, I mean, the way that the proof goes is by way of, oh, you know what? This should also have Caprace's name on it, because he wrote an appendix that kind of hit the last nail in the head or whatever. So super rigidity essentially gives you that for an irreducible lattice by way of bounded cohomology, bounded second cohomology, you can extend the action to one of the ambient factors for your, so here the ambient factor may be this one, but the automorphism group of a cat-zero cube complex is totally disconnected. And so that basically means you can't do that. So anytime you have an irreducible lattice where the ambient groups are have finitely many components, then you get this theorem. So I just chose a SL2C as an example. Okay, thank you. Yeah.
For that type of situation, is it an infinite problem whether such groups act freely on an infinite dimensional, horrible, terrible cube complex?
I think so. Yes. Is Elia? No. It's not purposeless. So these, right? We're in the world of median spaces. So these lattices have the Hagrup property, and as we saw in Elia's talks last week, having the Hagrup property means that you act properly on a median space. So he has the same result. Let's maybe not make that so fat. So Fioravanti has this result for finite rank median. And so certainly so we know that they act on a infinite rank median space properly. And so your question is, well, is it enough to look at an infinite dimensional cubulated space versus an infinite dimensional median space? And I think that's an open problem, but I'm not sure. I feel like Elia would know, but I don't think he's here. Okay. I'm always almost always in finite dimension. Other questions? Yeah.
The roller boundary to visual boundary. Components of the roller boundary always go to points.
Components. So if I take a single point from the roller boundary, then I associate a single point in the visual boundary. However, so there's kind of two different maps you can do. The one I defined will make it so that your image is equivalent, is the same for equivalent points, where 2 points are equivalent in the roller boundary if they're at finite distance. Was that your question? Okay, now you slowed me down. More questions? Should have asked that before. Okay, ask for questions before. Okay, so we're going to, the third application is to simplicialize the Tits boundary. That's what this C corresponds to. We had A, B, and C. When I first saw that, I was like, what? C what? Okay, so this is joint work with David Futer and Mark Hagen. So we're gonna slightly switch gears here from the visual boundary to the Tits boundary. I'm not going to give the topology on the Tits boundary, but it is different sometimes, most of the time, than the visual boundary on the set. Okay, and I'm noticing that this looks like it might read as differential topology, but it means different topology. Okay, so same set, different topology. And and so Mark introduced a boundary called the simplicial boundary. And I'm going to sort of sweep its role under the rug here. But the way that we're going to simplicialize the Tits boundary is very much, let's say, related to the simplicial structure on that simplicial boundary. It has a simplicial structure, and it's going to be most closely related to the barycentric subdivision, but it's going to be different. And it will be a homotopy equivalent to this. Okay, so the following exists. Again, X is finite dimensional. It's always been finite dimensional. So, excuse me. So I have my group here is X. We have another version for a subgroup, but for right now it's X. We're going to construct a simplicial complex called NT. N is for nerve, T is for Tits, and it's going to have an action by the automorphism group. It will be homotopy equivalent to the to the Tits boundary. And these two actions are almost commute, but they don't quite commute. So if I have the nerve, I can take the homotopy equivalence with the Tits boundary, or I can act via G. And we have not that the diagram commutes, but that they commute up to homotopy. Namely, those two maps are homotopy equivalent, are homotopic. So what is NT? I will give a brief description of what it is. So as its vertex set, we're going to look at the roller boundary modulo an equivalence relation. That equivalence relation will correspond to having finite distance, okay? And that finite distance is equal to the symmetric difference of those as sets. Remember, being in the roller compactification, I think of it as being a set. So that's that. And so, so that's going to be the vertex set. Secondly, we're going to associate to those classes a closed subset of the Tits boundary, and it's going to be just like before. And then you have to show that this is independent of the coset representative, which it is. So now we're going to connect to such sets if they have a non-empty intersection. That gives you an edge, and then I guess I should have said, then you connect them, you get two simplices when you have triples, non-empty intersection, and so on. So the standard construction. So then finite intersections give the simplices, where n, if I have n distinct things with a non-trivial intersection, then it gives me an n-1 simplex. So these give an open cover of the Tits boundary. Now, in order to make everything work, we have to restrict to a subclass of these classes, a special subset of these classes that are maximal and visible. So NT will be the geometric realization of this simplicial structure, and we have two nerve theorems, two equivariant nerve theorems that allow us to deduce that the that this nerve is homotopy equivalent to the Tits boundary. So one question is, why is it not X equivariant? And the reason is that the nerve theorem just doesn't give you equivariance on the nose. But then there's another issue that arises that I now regret not pulling up the picture for, since I have too much time, which is that the circumcenter can be on the boundary of this closed set. And this causes some issues because when you want to look at the nerve, so the two nerve theorems here are, one is for closed and one for open covers. And so passing between these closed and open covers, when the barycenter, when the circumcenter is on the boundary, causes some issues. So those are the two reasons why you don't get equivariance on the nose. And well, thank you very much.
Thank you. Does anyone have any questions?
Yeah.
This is also a question about something you said earlier, but like, why is the cube complex not when you rate to be at 0?
Oh, so Damian Osaida said that during a talk. He said they're not really cat 0, and that's his comment. But my interpretation is that they have so much structure, the median structure, the median algebra structure, the half spaces. It's just like very special, and so a lot of these techniques really explicitly use that the cat zero metric is like really almost an afterthought, right? So certainly here, there's, as you well know, a lot of cat zero geometry happening, but when you're looking at sort of the full power of what you can get out of a cat zero cube complex, the cat zero metric is like sort of not as high up as this like powerful machinery of this half spaces and the canonical association to complexes, etc. Was my interpretation of what he meant. You look like you have a question. No. Okay, more questions? Yeah.
Earlier on, you were talking about squeeze points.
Yes.
Are they related to Morse rays?
Right. So that's a good question. So the contracting Morse directions will be contained in the squeeze, whichever place that you put it. But these are small. I didn't mean to put the quotes in there. This is small in the sense that it can't carry a measure. I'm blanking on a word. You know, stationary. Thank you. Stationary measure, meaning that when you convolve mu with nu with mu, you get nu again. So they're too small to carry a stationary measure. So they do contain, the squeeze points do contain that, but it's a lot bigger.
So is it even bigger than the sublinear Morse directions?
Yes. Exactly. But we now know that if you were to, you can impose the sublinearly Morse exactly in terms of how the half spaces are connected. And now we know that that would be a smaller set where that stationary measure is supported. Not supported, but that it gives it full measure.
Just back something you said, by the way, this isometry going back, you said you had to take closures. What's an example of something where it doesn't?
I had to take closures. So you mean, yeah. Here are closures. I think what you're referring to was, so if I just stay, okay, let me come here. Yeah, so I think you're referring to a comment I made here possibly. So if I just take a random subset of X bar, okay, then I can look at all of the half spaces that contain it, and that will be consistent. However, the intersections of those may not equal C, but it contains C. And what is it exactly? It's the convex closure, it's the convex hull, median convex hull closed. So I think that's maybe what you were referring to. Yeah, thank you. Thank you.